In this video, we apply our understanding of the counting methods to some probability questions. This means deciding on whether to use the addition or multiplication principles, whether we use permutations, arrangements, selections, that sort of thing. I'll show you a framework to figure out how to determine which to use for any given scenario. Enjoy! Alrighty, so last version of this class we looked at each of the individual counting methods. We looked at addition rule, multiplication rule, arrangements, permutations, and then selections. So what we're going to do now is go through essentially a chapter that mix and matches the main approaches and applies it to probability, how we can use counting methods to calculate certain probabilities. So fundamentally, whenever we're trying to do a calculation for a probability, you need to know capital X, the number of favorable outcomes, and you need to know capital N, the number of total possible outcomes for the given scenario. So there is a fair bit of variance when it comes to this kind of area of study. However, there are three typical types of scenarios that come up quite often. The first is where choices in the sample space can be repeated multiple times. So if I'm creating a PIN code, for example, 4-digit PIN code, I could use the numbers 9999 repeatedly for that 4-digit PIN code. Under those circumstances, something like a multiplication principle would be most appropriate for calculating a certain number of combinations around that. If choices can't be repeated and the order matters, then you typically would use permutations in that case. So again, if I use the PIN code example, but I can't have the same digit being used multiple times, this is going to be an example of that because the order of your PIN code does matter. If you do 1, 2, 3, 4, you get a different outcome to 4, 3, 2, 1. And then lastly is if, again, you cannot repeat choices and the order doesn't matter, then you would use combinations or the selections equation. Those mean the same thing. That would be typically examples of teams of people. Because it doesn't matter if I say a team of Jack and Jill, it's the same thing as saying a team of Jill and Jack. The order in which I say those names is irrelevant. So we're going to have a look at a few different examples. This one here isn't quite a PIN code. This is just looking for the number of different 4-digit numbers that could be formed. So when we think about 4-digit numbers, there actually is an implied restriction in how we create that that number, and that is that any number can't start with a 0, essentially. And so that only gives us 9 possible options for that first digit, and then 10 for the remaining 3. Alright, because you've got numbers 1 through 9 on the first digit, then you've got numbers 0 through 9 for the next 3 digits. Since those are things that are made in sequence, you multiply all the way across. That gives you the total number of possible combinations as 9,000 in that case. And then the probability question might be something like, how many of these numbers are greater than something? That would be when you have to start looking at further restrictions and then calculating the probability based on that. Very similar example here, but we can't repeat digits. So again, we're going to have 9 possible options for that first digit. It's going to be our 1 through 9. But this time, whatever digit that we picked, so let's say we picked a 2, we can't use a 2 anymore in that second position. So instead of having 10 options for that next digit, we're back to having 9 again. But then from then on, the pattern then remains. We've chosen 2 digits, and then for the third digit, that means we've got 8 left, and then so on until you fill out all the positions there. You could do that using this approach here, where you just have 9, 9, 8, 7, or you could apply the implied restriction at the beginning as a multiplication of 9, and then use permutations for the rest of it, which is what I've described here. Both of these are equivalent, so whichever of those makes more sense to do, then go for that one. And then lastly, as I mentioned before, for For teams of people, you're typically using selections. Team of 3 boys, team of 3 girls, chosen from a group of 8 boys and 5 girls. How many different teams are possible? You typically do this implied in order. So it will be like choosing the boys first, then the girls, or choosing the girls first, then the boys. It doesn't actually matter what order you do it in, so long as you do it in an order. And so you typically just break it up into whatever the two segments and groups are. In this case, it's based on boys and girls. In other cases, it might be like choosing red blocks and blue blocks. It could be whatever. You just sort of do your selections equation for each individual subgroup and then multiply across. So in this case, we had 8 total boys. We're choosing 3. Remember, we've got 8 boys and choosing 3 of them for the team. So we use the selections equation. N is 8, R is 3. Very similar thing for the girls. There were 5 girls to choose from, and we're trying to select 3 of them. And because you made those choices in sequence, the multiplication principle applies. That's why you multiply these two results together, giving you a total number of possible outcomes of 560. So, in pretty much all cases, when you're trying to find probabilities, you want to start by finding your total number of possible outcomes. Then you want to find the total number of outcomes that are favorable. Capital NT, so finding your total number of possible outcomes, usually can be done pretty straightforwardly by using either multiplication, permutations, or selections. There usually isn't a whole lot more going on. We did see one example where there was a bit more going on. That was with the digits example. There was an implied restriction there. But in a lot of cases, you don't actually have that. The real issue really comes with finding your favorable number of outcomes, because you've got to apply further restrictions. But the good news is, once you have those two things, finding the actual probability is just a quick division. Nothing else is really going on there. So what I'll do is I'll grab a screenshot of that, and then I think the way that this will work best is I'll introduce the questions, and I'll just try and take you guys through the framework and apply that to each of the questions, and I'll field questions as we go through it, and yeah, we'll sort of take it that way. So we're going to start up with question 1. 4-digit number, no repetitions are allowed. Out of the digits 1 through 6, find the probability that the number is even. So you might know a quick shortcut for finding the probability that the number is going to be even. Does anyone know off the bat what probability that would end up being? Yeah, it does end up being a half. But for the sake of following the overall procedure that works for a lot of questions, we'll go ahead and figure out our total number of combinations and then the number of combinations for which there are even numbers. So if you wanted to find the total number of possible combinations in this scenario, it's 4-digit, it's no repetitions. What might you do?
Would you want to go down like the different digits and then multiply your amount of choices? Like you're going to start with 6,
Mhm.
and then since you can't repeat, you'll have 5 options for the next digit, and then
Yeah.
4 and then 3.
Yeah, precisely. 6, 5, 4, 3. So you can go down the list like that, or you can recognize its permutations. It's mathematically identical, either which way you do it. So you could do the 6 by 5 by 4 by 3, or you can do permutations N, P, R, which ends up looking like N as 6, and then 6 minus, we're choosing 4 digits. Yeah. I did just have to do a quick double take to make sure there was no issue with 0 there. 0 isn't one of our digits, so we don't have to worry about starting with a 0. But okay, and that does end up being 360, either which way you do it. So that's given us NT, total number of combinations, 360. Now for even. So how could we calculate the number of combinations which are even numbers?
Do we just half 360?
I mean, yeah, you could, because you know it's even and half of all numbers are going to be even. You could imagine that. Although, if I had said something a bit more complicated, I'm looking to see if we can do this in a way where we don't rely on intuition necessarily, like knowing that half of all numbers are going to be even. What makes an even number? Like, if I give you, I mean, even the one that we're seeing right now, 360, why do we know that's even?
Because it ends in 0, 2, 4, 6, or 8.
Yeah, precisely. So if we wanted to figure out number of combinations which end or which are even numbers, you would basically go digit by digit, focus on the restriction part first, and then backfill from there. So the restriction is we need an even number, and as we've just said, it's either 0, 2, 4, 6, or 8. Of those numbers that we actually have available to us, we have 2, 4, and 6. So that gives us 3 choices for that last possible digit. Yeah, so they're right, 2, 4, 6. That's 3 possible choices for that last digit. And then, yeah, so we've already decided that that last digit has to be ending in one of those. So all we're going to do now is backfill. So that means 5 for one choice, 4 for the next, and then 3. So 5, 4, 3, 3. Let me just double check that. Yeah, 5, 4, 3, 3. That's good. And that does become half of 360. If you were to calculate that out, we do get 180. So when we finally do our 180 over 360, that gets us our probability of a half. Obviously overkill for this, right? You wouldn't use this just for that question if you already know your even's going to be halves. But this is what you would use for more complicated scenarios. So let's see. Does that allow us to... Yeah, it turns out like questions 2 and 3, they have shortcuts that are readily available to them. We'll go through them anyway. If you can spot the shortcut off the bat, then let me know. But otherwise we'll do it using this framework. There's going to be plenty of other questions where we could use the more rigorous approach. So question 2. 3-letter words in quotation marks, are to be made by arranging the letters of computer. What is the probability that the word will start with a vowel? So when it says words, it just means a 3-letter arrangement of letters. Like COM, for example, is considered a word in this case, even if it's not in a dictionary. So if you can see a shortcut there, let me know. Otherwise, we could go through a more rigorous approach. Okay, if no shortcuts are found, then one of the things you can do is just start by figuring out what are the total number of combinations. So based on what we've got here, what would be most appropriate for finding total number of possible combinations?
Would you just do 9 times 8 times 7?
9 times 8 times 7.
I mean, sorry, 8 times 7 times 6.
Yeah, yeah, good point. Yeah, so it just becomes permutations 8 by 7 by 6, or yeah, multiplication principle, precisely. So yeah, that does, if you were to calculate that all out, give you a total number of combinations of 336. Cool. Then from there, we've got to figure out our number of desirable combinations, which in this case, desirable means that it starts with a vowel. So if we were to consider how to calculate that, remember we start by figuring out, by addressing the restriction and then backfilling from there. So if the restriction is starting with a vowel, we need to consider how many choices do we have for that first letter. What's that going to be?
3?
3, yeah, precisely. We got 3. So by choosing 3 to start with, we can now just sort of backfill from there. So if one of the vowels had to be chosen for that first digit, then what does that mean for the remaining 2? Well, I should say letters instead of digits, but yeah. What does that mean for the remaining 2 letters?
There'll be 7 and 6 options left.
Yeah, 7 and 6, because we've chosen one of the 8. Even though it was a vowel, it doesn't really matter because we've chosen one of the 8 that were there. Yeah, precisely, leaving us with 7 and then 6 because it decrements.
Chris, I had one question, right,
Mhm.
about like the wording of this question too. Like, it doesn't really specify if you're allowed to repeat it or not. Or are you meant to like deduce by saying when it says like arranging the letters of the word, does that mean like you can't repeat it? The letters?
Yeah, I think the intention of the writer was to imagine it like Scrabble, where you've got this Scrabble bag of the letters computer, and you can only pull those letters out of the bag. Um, I think, were there any duplicate in here? COMPT. There weren't even any duplicates here. I know sometimes they, yeah, not even here actually. Sometimes I pick a word that has duplicate letters in there, and that's definitely a dead giveaway that um, that repetitions aren't possible, because if you have duplicate letters, then um, yeah, yeah, I guess this is something you just sort of look at the first time and then you realize that that's the trend forever, which is if they're saying arranging letters in a word, it's implied that it's sort of like Scrabble. Yeah, I can see how that'd be confusing. But yes, that is how you'd handle that. And if you're in a scenario in an exam where it's not quite like this and it's ambiguous, just write a quick thing saying, hey, these are my assumptions on what you meant. You can get away with that a lot better in the SACs because you can just sort of ask your teacher, but in the actual exam, that comes a bit more challenging. So you can write a little thing saying, hey, these are my assumptions going into it, and that gives you the best opportunity to get a consequential mark out of it. But yes, we got our 2 calculations there. 336 for total number of outcomes, 126 for desirable number of outcomes. If you divide those 2 things together, you get 3 out of 8 as a final probability. I'm curious, now that you see that probability, does anyone see a shortcut as to how we could have done this?
When we had like 8 times 7 times 6 over 3 times, I mean 3 times 7 times 6 over 8 times 7 times 6,
Mm-hmm.
could we have just cancelled out the 7s and the 6s and then we would have gotten 3 over 8?
I mean, yeah, that's also a good point. So it might even pay off to not even bother doing the actual multiplications and just do some cancellations. Absolutely. Yeah, that is a good answer to that. What I meant when I asked though was to avoid this whole combinations approach where we calculate total and desirable. Is there a thing you can look at here, especially considering you see 3 out of 8, how you could at a glance know that probability?
Oh, wait. So since the word needs to start with a vowel, we don't really need to care about the next two letters. So
Yeah.
we could have just like looked at it and thought there's three vowels out of eight letters.
Yeah, correct. 3 vowels out of 8 total letters. It's going to be a 3 out of 8 chance of starting with a vowel. That is the shortcut. But again, the whole point of what we're doing here is to see, hey, if you don't see any immediate ways of going about it, because those are hard to find, right? It's very case by case. Whereas this, it's very, it's repeatable in a lot of scenarios. That will set us up nicely for question 3, though. So either let me know total number of combinations, or show me what the shortcut would have been for 3. One out of 5? Yeah, correct. Exact same logic, right? Starts with H, starts with vowel. Those are basically the exact same question, except there's only going to be one H in there. Yeah, that's that one. Part B, letter H is chosen. Still has a shortcut there, but it's not as obvious. So again, either total number of combinations, or if you can get it outright, that'd be good as well. I suppose the other good thing about doing it the framework way is that when you've got multiple like sections, you can reuse your total number of combinations multiple times across all parts. So that's another slight advantage you'd have. (47 over 60). Let me simplify that just in case, but I don't think so. 47 over 60. Nah, that's a bit off. Where did you get 47 from? Because getting it over 60 sounds fine. 47 is just a weird number.
I just added the like I added 1/5,
Mhm.
1/4, and 1/3.
Oh, he did 1 over 5, 1 over 4, 1 over 3. Okay. No, I like your idea there, but letter H being chosen at all, um, adding them together. When you add, so addition principle just means you're considering mutually exclusive choices. So the example I gave was like ordering a meal at a restaurant. You've got pastas, you've got pizzas, you've got entrees, you've got whatevers, right? You're only ordering one meal from that restaurant. So it doesn't actually matter what all those subgroups are. They're all just of the main group of meal, and you just add each of the combinations of the subgroups together. Similar thing here, where we've got essentially 3 separate subgroups. You can either choose a H in the first position, in the second position, or the third position, but not in an order. They're all mutually exclusive. You can't put a H in all those at the same time. And so for that reason, instead of doing a fifth plus a fourth plus a third, it's a fifth plus a fifth plus a fifth. It doesn't actually decrement because you're looking at them individually as if they were 3 separate possible I was going to say timelines, but like three possible scenarios that could have been. Is it clear why we do it that way rather than decrementing? Yeah. Okay. Cool. So that's the shortcut way of doing that one. Otherwise, yeah, you could calculate combinations for each of those. It's a similar idea again, which is if you want to calculate combinations for H being in the first slot, you focus on it's basically guaranteed, right? It's one possible option for that first slot, and then four, and then three. Otherwise, in the second slot, that one's the fixed one. Then four and three either side, and then so on and so forth. Yeah, so that's that. And next up, so this one I believe doesn't really have, or at least I didn't find a shortcut for this. Both vowels are chosen. So you can try and see if you can find one if you want, but I don't think I was able to find one. With that in mind, either final answer or we'll do total number of possible outcomes. If you need me to jump in, let me know. Otherwise, I'm happy for you guys to keep working on it yourselves. As a hint, this one can kind of be thought of similar to the team selection exercises where we're choosing boys and girls. We're now choosing vowels and consonants, really. That could be one way of thinking about this. Although it's worth pointing out that in the team exercise, we had selections because the order didn't matter. In this case, we have permutations because the order does matter. So that does make a bit of a, or give us a bit of a nuanced approach to what you'll be doing here, but overall the structure will be similar. I'll leave that as a hint. And if not, just tell me to jump in and we can do it.
Chris, is the probability 3 out of 10?
It is 3 out of 10. Hell yeah. Got it. I'm keen to hear the approach.
So, first I did like the total possible outcomes,
Yep.
using like the permutation equation.
Yep.
So 5 factorial over 2 factorial, which gave me 63 letter arrangements.
Yep. Yep.
And then like I was looking at, I just thought like if it's 3 letters, right, and 2 of them have to be vowels, that means you only have like one more spot for any of those other letters.
Mhm.
That means you're gonna have like 3 sets of letters.
Yep.
It's either gonna be H, R, and T with the 2 vowels, right? And then because you can arrange those sets in different ways, you do 3 factorial,
Yeah.
which gives you like 6 different arrangements for each set.
Yeah.
And then if you have 3 sets with 6 arrangements, that means you've got 18 like different like possible ways to arrange those 3 letters with 2 vowels. So if there's
Mhm.
18 ways out of a total 60 like outcomes, that means your final probability is 3 out of 10.
That is good.
It's a
Um,
little bit brute force, but like
no,
yeah.
that's not even brute force. I don't think that is pretty much what I have written in my answer. Actually, I guess all I'll do is I'll expand on that a little bit. The reason why, I mean, I kind of did a little quick drawing here. The reason why this isn't super accurate is because you can't really think of it as vowel, vowel, consonant. You have to think of it as vowel 1, vowel 2, consonant, and those can be done in any order, which is why you were correct, where you have to then do a further factorial to rearrange from there. So that is correct. That is a good way of doing it. Um, yeah, I mean that is correct. Doesn't need to be clarified further. I know you obviously got it, but I'm happy to expand that on paper, or I guess on phone if I need to.
Yeah, could you please do that? Because if I was to probably do what I did on like a test, it like my teacher probably wouldn't understand. So
Sure. Okay. No, fair enough then. So first things first, you did good with calculating your number of combinations. So that gives you the 60. So you could say NT is 60. Then when you're calculating like desirable number of outcomes. The example I gave before about the teams is what I'll approach this in by saying you can imagine choosing figuring out number of combinations of how you could select vowels and then number of combinations on how you could select consonant. So because we're using permutations here, let me just double check where they were. So we had EA, yeah, we had two vowels, and yeah, we're choosing from two vowels that exist, we're choosing two, but we're using the permutations version of that. That gives you the 2 factorial over 1 factorial, or hang on, yeah, 2 factorial over 0 factorial actually, but ends up being the same thing. Point being, it's 2 by 1, which gives you the 2. Then for the consonant, we have 3 and we're choosing 1. 3 choose 1, that's the same thing as literally just 3, because it's 3 factorial on 2 factorial, the 2 and the 1 cancel out, giving you a total of 3 there. So that gets you the individual groups of the 2 and the 3. Are we clear on that so far?
Yeah.
Okay. And then the last thing to do is consider how you could actually arrange these from this point onwards. So you got 2 ways you could arrange the vowels within themselves. You've got 3 ways you could then further arrange the consonants. But the thing is, you can then distribute these things through the grid. I like drawing a little grid of like vowel 1, vowel 2, consonant, and so on. Basically, you have your 2 by 3 giving you 6 for this specific section, but you can do that in a further 3 separate ways, basically. And that's really all it boils down to. You do your 2 by 3 here to get the 6, and then because these have 3 further positions they could be arranged in, you do a further multiply of 3. Total was 60, and then once you simplify that down, it is just 3 over 10. It's a tough one to explain. I get why you're concerned that the way you write out would be a bit weird, or at least wouldn't look great. Because even this, how I've written it out, doesn't seem to have much flow unless I verbalize it. I mean, I'll show you what I wrote. That'll hopefully... it wasn't the same analogy, but it was enough to where I said, look, both vowels chosen means 2 of them are taken up by the vowels, 1 is taken up by the remaining 3 letters. This is your vowels being chosen in any order. This is the consonant going in any spot. That gives you the 6. And then lastly, because that consonant, you could think of it as like where you put the consonant, basically. It could be in any 3 positions, which means a further multiply of 3. That's the whole, you've got 3 separate mutually exclusive outcomes that you're repeating. So that's how I've explained it. I guess you've got 2 ways of the explanation. One is like the team way, and one is, well, this. Is that clear enough? It's a tougher one to explain, definitely. Alright, if there's no further questions, let me see. Yep, the screen shares back to where it should be. 3 men, 3 women are to be seated randomly in a row. Find the probability that both of the end places will be filled by women. Let me see, did I find a shortcut for this? Maybe. I didn't write a shortcut, but the final answer seems like it could be. Maybe. Anyway, so either I'll take either final answer or we could do it step by step. So either have at it or let me know. In fact, I'll just be one moment. And I'm back.
Chris, can we do this step by step?
Certainly.
I figured out that there's 720 ways to fill the 6 seats, but
That is correct. How did you
um,
come to that conclusion?
just 6 factorial.
6 factorial. Yeah, so we can't reuse the same people at multiple spots. Therefore, like that's the whole decrementing every single time. We can't reuse them. So yeah, got capital
And
NT.
also, I'm guessing that like since there's 4 people, when if we have 2 women on the ends, that means we've got 4 remaining people. So the the probability that there's 2 women on both ends is probably like 4 factorial multiplied by some other number. But I'm trying to figure that out right now.
Yeah. Yeah, no, you're right. 4 factorial is going to be part of that. That's the remaining 1 woman, 3 men. Yep, that gives you the 4 factorial. Typically, the way I think about these is I think about the restriction first. And in this case, the restriction is that the end places have to be filled by women. So if you just had to fill the end places with women, how many ways could you do that based on what you have available to you? Yeah, like if the whole question was just I have 3 men, 3 women, and I will have 2 spots to be filled with women, how do you do that?
You just do 3 factorial.
3
I mean,
factorial.
sorry, two factorial. My bad.
2 factorial. Why not 2 factorial? No. A 3 factorial is closer. Yeah, 3 factorial is closer, but not because it's 3 factorial necessarily, but because the multiply by 1 just doesn't do anything. Basically, you've got 3 women and 2 spots to put them in. So there's 3 possibilities for that first slot, and then 2 possibilities for that second slot. You don't really consider the final multiplication by 1 because it doesn't really do anything. So yeah, it ends up being the permutations equation. You've got 3 women that you're choosing from, 2 positions to put them in. That does end up giving you a total of 6. Then from there, you backfill. So we found our combinations that put women in the end seats, and you kind of already gave the answer to that one, which is well, I'll let you say it again.
If the like 2 seats are already filled with women, then there's 4 people left.
Mhm.
That means to figure out the multiple ways to arrange them, you do 4 factorial.
Yeah, correct. And this is done in sequence. We seeded the women first, and then we seeded everyone else. So we got the 6 combinations from the first bit, and then multiply by a further 4 factorial, which 4 factorial is 24. So you do 6 by 24. That was supposed to be a 24. Jesus. 6 by 24, which is 144. That gives you your numerator. This is our denominator. And then once you do that simplification, it does end up being a fifth. So the neatness of that final answer probably implies there's a nice little shortcut way of doing this. Is there? Yeah, I don't know. It is a neat answer though, so I'm sure if you go digging deep enough, you might find a nice rationalization. Anything to clarify further about that one? If not, make a start on question 5. Actually, that one's going to take a while. I do want to address this question 6 because it is quite unique. So we'll skip question 5 for this one. That's going to take a fair bit. Question 6 being unique, I think, is worth focusing on. So we'll do that. So either have a think about it yourself, and I think I mentioned this last time we went through this in the, it would have been the class 3, one of the class 3 sessions we did. I think I mentioned how to handle question 6. Does anyone remember what I said there?
Was it to draw a or like think of like a tree diagram?
Tree diagram, let's see. Can this one be a tree diagram? Kind of. It could.
Because it doesn't specify like how many uh like stages of choice he gets. Like he could
Oh,
only have ham, or he could have like all 6 of those like
mhm.
ingredients plus ham.
Well, it does actually. How you've described it does actually tell you how many stages of choices he has. He has one choice here, he has another choice to make here, so on and so forth. Each individual ingredient is either a yes, no. So yeah, you actually are, you've actually identified that yes, there are multiple stages there. And you could tree diagram that, I guess. You either have lettuce, no lettuce, then you have tomato, no tomato. That'd be a lot to draw. It does end up being, because that's 2 to the power two, 1, 2, 3, 4, 5, 6, 7, 8. 2 to the 8, so 256, which would not be great to draw. But yeah, that was the thing I wanted to identify, which was a bit harder to see where the choices are. The choices are in the yes, no on each of these individually. There is another trick that's in here. I think it's more of a wording trick than anything else, so I'll kind of just give this away, which is the sandwich has to have at least one ingredient in it. It's implied in the question that you're supposed to have at least one of these ingredients in it. To me, having 2 slices of bread isn't necessarily not a sandwich, but according to the book, apparently, if you don't have anything in between, it's not considered a sandwich. Because if I didn't say that, you might be inclined to think that 6A would just be 50-50. Because if all of these are 50-50 choices, then when you get to the ham, you either have it or you don't. But one of the things that's a bit weird about this is that you have to have at least one of these ingredients. So instead of having 256 total possible outcomes, which is 2 to the 6th, it's 2 by 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 2. We have a slightly different denominator. Anyone have any ideas how you'd figure out total number of combinations if you have to have at least one ingredient? It's an approach we haven't talked about today, but we have talked about in previous lessons about probability fundamentals.
Since the order doesn't really matter, do we use selections equation?
Well, selections would imply that the number of choices decrements every sequence. Like, 'cause it's based on the fact that you go from your factorials, right? Which is I have 8 ingredients, then I have 7, then I have 6, then I have 5. How does that work? Why is that not good? You might be able to do this with selections because you have 8 ingredients in total. You're selecting either 1, 2, 3, 4, 5 with no. You might be able to do it. I'm struggling to see exactly how, but you might. The thing I had in mind is probably a bit more, probably a bit easier, which is to use a complement probabilities approach. So if I once again screen share the answer section, when we're finding our total number of possible combinations, it was without any restrictions, it will be 2 times 2 times 2, 8 times, because you've got 8 combinations. You either yes, no on lettuce, yes, no on tomato, yes, no on carrot, so on and so forth. But because we have to have at least one ingredient in there, then we have to. One of the easiest ways to go about this is to just subtract the number of combinations that have 0 ingredients in them. And there's only one way of doing that, which is if you say no to everything. There's only one way of doing that. So instead of having just 2 to the 8, you now have 2 to the 8 minus 1. That gives you total number of combinations. And from there, the rest of it's not so bad anymore, because you just go back to what I said before, which is if you want to find the probability of containing ham, then ham is guaranteed. So you go 2 possible choices for lettuce. It's either yes, no, 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 yes. So instead of having all 2s, you now have all 2s and a 1, which is why it's 2 to the 7 instead of 2 to the 8. Normally that would simplify down to a half, but because you've done a subtract 1 on here, it's basically almost a half, but not quite. Clear enough on that approach there? Yeah, I hesitate to say that selections could work. It might, I just haven't crystallized what that looks like. So if you want to maybe try that yourself at some point, see if you can figure out a way to get here with selections, then that will be pretty cool if you could do that. But yeah, I personally didn't. Okay, so I'll screen share back over. Yep. And then from there, contains 3 ingredients, contains at least 3 ingredients. Let me double check to see if that's anything special. Yeah, okay. This one can be using the counting methods as opposed to the slightly unique way we had to do it the first time. Parts B and C could use counting methods. I think I'll only get you to do B, and then we'll talk about C. There's a lot in C. I think the issue with trying to use selections, at least in the previous example, was that each of the ingredients were named. So it's like it's not just that we have 8 ingredients. We had very specific ingredients there. Whereas in other applications, it was like we have 7 blocks, or there's 3 girls, or there's whatever. It's all ambiguous under the group of just that group. Whereas here, since they were all named, I think that's where it gets a bit more nuanced. Which is why when we have a look at part B, instead of naming the specific ingredients, we just say 3 ingredients. That simplifies things down to just your counting methods approaches. We are getting pretty close to end of class on this one. Does anyone want to jump in and try explain up to where they're up to, or shall I just go for it? Okay. So what I was trying to explain there is because we're now at a stage where we're just considering ingredients in total, we can now refer to our selections equation. So you actually did bring that one up before, which was a potential way to do this. Because we're now referring to just the ingredients themselves, where you have 8 total ingredients, and since we need to select 3, then you would use your selections equation. The reason why it's selection is because the order in which you have those ingredients in doesn't matter, and you can't have repeats. That gives you 56 outcomes out of a total of the 255 that we got as our total there. The part C was to have at least 3 ingredients. 20-second question. Anyone know how you would adapt the answer to part B to part C? It's an approach we've used before today. Okay, so it's basically where you look at each thing as mutually exclusive. At least 3 ingredients means either 3 or 4 or 5 or 6, so on and so forth. So that's one way you could do it. You just do the NCR equation for all of those and then add them together. Or you could save a little bit of work and use complement probabilities instead. So instead of doing 3, 4, 5, 6, 7, 8, you could do 1, 2, and then subtract that from total, rather than calculate all the way upwards. That gives you a much fewer amount of combinations or amount of calculations to make, and both get you to the same spot. So, if I need to clarify that any further, feel free to stay behind. Otherwise, that'll be it. Take care.